Okay, hi class. This video lesson here, we're going to just do a bit of a review of the amount of an ordinary simple annuity. I just want to make sure you're comfortable using this formula before you go ahead. Sometimes when we study these annuity problems, after a while the formulas start to look the same and the problems start to look the same, and it can be difficult to tell which one applies and how exactly they're different. So to start, when we are calculating the amount of an ordinary simple annuity, the conditions are the payment interval is the same as the compounding period. That payment is made at the end of each compounding period, and the first payment starts off also at the end of the first compounding period. So these are regular deposits that are being made, earning interest and accumulating to some future value. So we can kind of make that connection between the annuity formula and the compound interest formula, where this compound interest formula here could also be rewritten as future value equals present value multiplied by our exponential part. When we are dealing with an annuity, of course, we're dealing with the sum of a whole bunch of terms, and the value of those terms is obtained using the compound interest formula here. Now, when we look at a different type of annuity that involves a single payment at the beginning, or a single loan amount or a single investment that pays out multiple amounts over time. This too is an annuity, but it's a little bit of a reverse annuity. The money has to be there up front in order to fund or provide for this payment plan, or an initial amount has to have been withdrawn for a loan and now we're paying it back. So in this lesson, we're going to be looking at the present value of an annuity. We'll develop this formula and use it in this lesson as well. And the terms that are used in this formula, the quantities, are very similar to what was used in the amount of an annuity formula. So there's going to be some similarities here that will help us to learn this new formula and see the application for technology is also present when we're using the TVM solver. You've had a chance to do that already, so you know about the apps and the finance menu there for using technology. So let's start out with the scenario here, which is shown in your textbook on page 419. It introduces a situation where someone has won a lottery and they have an option to receive $2,000 every 2 weeks for 20 years. So here we have money coming out into your pocket, $2,000 bi-weekly for a length of time, 20 years. So in this case, the money is not being invested every 2 weeks for 20 years. It's money that's going to be paid out to the winner. Now, what we're exploring here is specifically what would be the equivalent cash payment given to you right now that would be equivalent to an investment earning compound interest and providing for those payments over time. So how much would you have to have right now in your pocket in order to be able to invest at, in this case, we were given a 5.6% annual interest rate where compounding was biweekly. So there's different strategies which we can explore. In each case, we're going to let PV be the present value of the cash payment. We're going to explain what's being done in each strategy. These are sort of prepared for you. We're going to complete the calculation, and then we're going to identify whether this is more or less than the actual cash payment for the payday lottery. We're told that amount in the scenario here. The amount is $625,000 given to you now. So the lottery company would be willing to write you a check for $625,000 right now, or pay you $2,000 every 2 weeks for 20 years. And the question is, are those equivalent options? Which one would you prefer is a different question to answer. So as we explore the first strategy here, we're going to see that the calculation is sort of set up for us. We have $2,000 per bi-week every 2 weeks. There are 26 biweekly periods in a year and over 20 years. So what would that calculation yield? Well, it would yield an amount, which in this case is $1,040,000. What would that amount represent? Well, it would represent your total payout to you. There's no interest really involved in this calculation. There's no sense that there's compounding involved, so no interest being applied. Clearly, it's quite a bit more than the equivalent cash payment given to you right now. Okay, so this is an overestimate. We wouldn't expect to be given $1,040,000 now. If you saved all those $2,000 payments every 2 weeks for 20 years, it would amount to $1,040,000. But that's not what the lottery company is going to give you at this point, because that amount, if it was actually invested, would earn a lot more interest, and so that would increase the value of the winning. The second strategy takes that amount. Okay, so $1,040,000 is going to be paid out, but what if it was paid out once at the very end? So we can use our present value compound interest formula, which instead of dividing by 1 plus I to the n, can multiply by 1 plus I to the negative n. It's equivalent. In this case, we're going to calculate the term interest rate by dividing the annual rate by 26. We're going to multiply the number of compounding periods here with number of years by times per year. So we get 520 compounding periods. We're going to get a decimal value for the term interest rate, which we always have to use as a decimal. So 0.056 is our annual rate as a decimal. Dividing that by 26, we get 0.002154. Okay, so this is the term interest rate. When we calculate that present value, we'll get how much would need to be put in to an investment right now once in order to pay out $1,040,000 in 20 years. Okay, so it's actually a fairly small amount. It would only take about $340,000 invested now over 20 years with 520 compounding periods during that time would grow to $1,040,000. So this would represent a single investment now, and it would involve one amount at the end. So rather than receiving 520 amounts every 2 weeks, you're only getting one amount at the end. So clearly this is not accurate. It turns out that comparing to the equivalent cash payment, it's too low. So I would not choose this option. Someone gave me $340,000. That would not be equivalent to $1,040,000 at the end. So the answer here lies in the fact that we're dealing with multiple withdrawals into your bank account from some initial amount that's paying out a little bit at a time. And so every 2 weeks, the amount in the investment is depleted by $2,000, but it keeps earning compound interest until at the very end, it's paid out the last $2,000 and you have your $1,040,000. So what amount would actually be more accurate? Well, if you take the amount that we obtained from strategy number 1, which is way too high, includes no interest and is a single total payment from all of the 520 values, then if we average that with the amount that is calculated in strategy 2, which is a single investment, one amount paid at the end, we get something pretty close. So this amount, which is an average of the total payout and a single principal which grows to that total payout, this is a little bit too high. So none of these strategies really are adequate in calculating the single cash payment now that provides for those 520 payouts. But the last strategy comes the closest. Really what we need here is something which involves a little bit more math power. So we're going to need something with some computational strength here. So I'm going to use a spreadsheet. I'm going to explain how we can use a spreadsheet here to solve this annuity problem. Okay, I've opened up this file called Investigate Present Value Chart. And at first, you need to take note of some things. So here off to the side, we have the fixed amount, the annual interest rate, the compounding frequency, the term rate, and the number of compounding periods. Those are all calculated separately, just as you would set up if you were solving a problem by hand with a formula, and that's a good practice to show how those are calculated. I'm also doing that because it allows me to use those numbers in some of the formulas in the spreadsheet. So on the top left, we have the total present value of all of the investments that would produce these regular payments of $2,000. And that, of course, is the actual present value of this annuity. It's the amount at present that would need to be provided in order to make possible these regular payments of $2,000. The total payments is $1,040,000 that's shown there. That's my 520 payouts. And in the first column, below that, we have the number of bi-weeks from present. So this is the number of 2-week periods from right now. So 1 2-week period later, we have the need for a $2,000 payment to be made. How much would need to be invested at present in order to provide for that? So what we're doing here is we're going to use the present value calculation, which is the amount that needs to be obtained in the future divided by 1 plus I to the n, or we can use 1 plus I to the negative n and multiply. And in this case, $1,995 is the amount at present that would need to be invested, or the principal value. So the present value there, after having applied compound interest at that interest rate, 0.002154, for 2 weeks would amount to $2,000. If we look at what would be necessary to put in right now in order to pay out $2,000 4 weeks from now, well, it's a little bit less. You have more time to earn compound interest, so the present value decreases, 1,991. And as we go down this column, we find that each of these entries here is the amount at present that would need to be invested for this number of biweekly periods in order to accumulate to $2,000. The total of all of these principals is going to be the present value of the annuity. It would be the total sum of all of these, and you can see what happens as you go down. At each given time, the present value is shrinking, because if something needs to be invested for 260 biweekly periods, that's about halfway through exactly our payouts. It still amounts to $2,000, but only $1,143 would need to be invested at present in order to accumulate to that $2,000 amount. So as we can see, we go down to the very last investment here, and we see that to invest $653.35 right now in 520 biweekly periods, that would accumulate to $2,000. And in the third column, it's just the calculation of that present value with interest over 520 biweekly periods would obviously, they're all giving 2,000. So the sum of this second column is what we really were dealing with when we talk about the present value of this annuity. $625,232.20 would need to be put into an account right now in order to make possible all those payments. The option is maybe taking that $625,000 and giving it to the person directly and letting them make that same investment. But that's the equivalent value to receiving 520 $2,000 payments. So obviously there's a difference there, and that's due to the interest that's earned. So you could go and put in $625,000 into your bank account right now, and that would accumulate to 56 or 520 payouts of 2,000. So let's go back here and sum up this formula. Okay, here's the present value of an annuity formula. The total of all of those investments at present gives this value. So R is the regular payment in dollars, PV is that present value, I is the interest rate for the compounding period as a decimal, N is the number of compounding periods. So it's same as the amount of an annuity formula that we saw earlier. Slight difference, of course, we have subtraction in the numerator, we have a negative exponent in the numerator, and of course this gives a different calculated value. So we can't use this to calculate what the future value would be of many regular deposits. It won't work. The conditions there are the same as before. When we apply this formula, we can do this by hand or we can use the TVM solver. So let's have a look at that. So the present value of this annuity, put the values that you know, the regular withdrawal, the annual interest rate divided by the compounding frequency, and I would just take note that this is approximately equal to. What I would do in your calculator is store this value somehow in a memory. I can show you that in class how to do that. The number of compounding periods shown here. Include the formula. You'd be surprised how quickly you'll memorize a formula. I'll provide this on an exam, but just for using it in class and on your feedback problems, it won't take very long before you'll have memorized that just from having written it down every single time. Substitute the numbers in and show just at least maybe one intermediate step after that before the final answer. And you'd be surprised if you're rounding these values here. If you're rounding that value, that 0.002154, you'll get quite a bit different answer in your final value. So that's where storing your I value in memory is very useful because it'll avoid rounding errors. So that's the use of the formula. It matches our spreadsheet. Now we'll show the use of the TVM solver. So here in this app, again, we've used this before, so we're able to load in what we know. Here you can do a calculation right in the space provided, so 26 times 20 gives you the 520. Remember to include this as the annual interest rate, 5.6. The present value, we don't know, so just leave it at 0. The payment to you is $2,000. Future value is 0 for two reasons. We don't know the value, but at the end, there's nothing left in the account, or there's nothing left to pay out. So 26 times per year, compounded 26 times a year. Payment is received at the end of every 2 weeks. So now we go up to the amount that we're trying to solve for, which is the present value. Alpha, enter, solves it out for us. In this case, it would be a negative because here someone had to pay this out of pocket in order to invest it. In this case, came from the Lottery Corporation, but it had to have been invested, so it's a negative value. So just looking at some applications of this, there's different scenarios where you're going to be using the present value. Some might involve retirement savings, some might involve a certain payout for a kind of a contest, some involve loans. So in this case, providing for an annuity is an investment. So the $700 is the withdrawal, so that's going to be your R value. At the end of each month, so that tells you that the compounding frequency is 12 for 8 months, starting 1 month from now. Annual interest rate is given at 5.4%. Your compounding is monthly. That matches the frequency of the withdrawals. And the question here is, how much must Victor deposit in his bank account today? The keyword there is today, which means the present value is the unknown. So in this case, you're looking at the use of the TVM solver potentially, or the use of the formula. Here, for these ones, I'll just set up what we know, and I'll use the TVM solver to solve for this one. The TVM solver will take in the annual interest rate, so it would be simple to use this for a problem like an investment. So we'll change this to 5.4, and we're going to put in here monthly for 8 months. So this is 8 number of compounding periods. The present value is unknown. The payout is $700. And it's a positive amount. The future value is 0, and it is monthly, so that is 12 times a year. So here we go back to the present value and solve for that, and we get a amount today that would need to provide for that would be $5,488.28. So that would be the calculated PV value. Okay, so here's another situation where someone wants a retirement plan, and they're going to put in a certain amount of money. The regular deposit is equal to $7,500, or regular withdrawal rather, every 3 months, so it's quarterly. Quarterly withdrawals would match quarterly compounding. This is the annual interest rate, and the amount N would be 25 years times 4 times a year, which would give you 100 compounding periods. So again, here I'll use the formula. So in this calculation, substituted the values I knew, did one intermediate step, calculating the biggest part, which is what's inside the brackets, and the final answer to the nearest cent is 297,313.05. Repaying loans is another application for annuities, so we need to know that sometimes it's a withdrawal, sometimes it's a withdrawal from your account because you made a loan and it's being paid out. So in this case, these payments are also form an annuity, whose present value is the principal borrowed, or the loan amount. When all the payments are made, both the principal borrowed and the interest due will have been paid. And the main thing to remember in all of this is that your interest, which is either being earned or which is being charged as a result of the loan, is always the difference between the present value and the number of regular withdrawals or payments, which is exactly the same as what we saw for the amount of an annuity, where it was the difference between the future value and the number of deposits times that amount. So we can calculate that in questions like this one here: how much interest will CIMA pay on the loan? Okay, so as I've set this problem up here, we have the annual interest rate as a decimal, we have monthly compounding, we have 36 compounding periods, and a $300 loan payment per month. So entering these values in here, we're going to go to the interest rate and change this to 6.9. We can leave the present value, which is the amount that you could afford to borrow. That's going to result in these $300 monthly loan payments. The payment amount is, in this case, $300. Because this is coming out of your pocket, it's a negative value on the TVM solver. The future value is 0. At the end of the 36 payments, you owe nothing. And of course, the compounding is still monthly. So we go back up to the present value and find out what you can afford to borrow that would have you paying $300 a month. In this case, you could afford to accept a $2,339.07 loan if you were actually only paying out over 8 months. But in this case, it's 36 months, which is going to change the principal borrowed by quite a bit. So let's resolve for this one, and the loan amount be much higher. $9,730 would be the present value. Of course, the interest here would be the difference between what you borrowed and how much you paid. Now in this case, actually would have to adjust this formula because I can see that the order here needs to be changed. The number of payments multiplied by the value of each payment, subtract the present value, would give you the interest earned, because of course that would be a larger amount here. So in the amount of an annuity, you have regular deposits are accumulating to a total value with compound interest, and the difference between the future value and that would give you interest. But here we're going to have paid out 36 times, and each time we would have paid out $300, and that's going to be greater than the principal amount borrowed, which was $97,30.34. So in this case, $10,800 are the total payments. The loan amount was less than that, and the fee to borrow that amount without paying for it up front is the interest, that would be $1,069.66. Okay, this concludes video lessons for the present value of an annuity. You can see the assigned work down there. Numbers 3 and 5 in the part A require the TVM solver. The remainder of the questions should be solved with the formula. See you in class.